Good afternoon, everyone. For the next session, we have Professor Dr. G. Sitharaman, Head of the Department, IIIT Tiruchirappalli. Professor has experience in teaching as well as in administration over 21 years and has served different roles: Secretary in Aravalli Foundation, Puducherry, as Registrar in NIT Puducherry, and as Associate Professor in NIT Nagaland, and Professor and Principal in OEC Trichy. Dr. G. Sitharaman has experience in teaching during research over 4 years as a research associate and laboratory engineer at NIT Trichy. Coming to academic responsibilities, SAR has served different roles like Directors Advisory Committee, APIC Chairman, TEQIP Coordinator, Dean Research and Consultancy. Dr. G. Sitharaman has produced 3 PhDs and currently 3 scholars are pursuing PhD. Nearly 55 lakhs funds has been received over research proposals and fundings. Coming to publications, Professor has published nearly 17 international journals and more than 30 IEEE conferences. 8 number of STTP programs has been organized and received funding of over 30 lakhs. National and international conferences has been organized in 2 numbers. Center of Excellences in VLSI lab and ASIC CAD lab has been established. Over 7 countries SAR has visited, delivering keynote speeches like UK, USA, Japan, Hong Kong, Malaysia, Singapore and Indonesia for delivering keynote lecture. Now in this session, SAR is about to handle architectures of FPGA and features available with Xilinx and Altera. FPGAs related to IoT applications. Over to SAR.
Good afternoon to all. I think my screen is visible to everyone.
Yes, sir, visible, sir.
Okay.
Sir.
Okay, thank you for the introduction. Today I'm going to present a topic on FPGA architectures and features available with Xilinx and Altera FPGA. So I'm going to explain the architecture of Spotron 2 FPGA. Even though we have nowadays Vertex and Zinc FPGAs, but the architecture wise everything is same. So Spotron 2 is a 6-member family. So it is a Xilinx FPGA. Actually there are 2 vendors, one is Xilinx and another one is the Altera, most popular in the market. See what is the main advantage of this VLSI design is either we have to increase the speed. The objective of VLSI design is to increase the speed and reduce the power and reduce the area. So previously the people are looking for all the 3, that is to increase the speed, reduce the power and reduce the area, that is number of logic gates. But nowadays we have billions of transistors are fabricated on a single chip. So the researchers are mostly concentrate on to increase the speed and reduce the power. So in general, in VLSI design, there are several techniques are available to increase the speed and reduce the power. So one type is we can use those technique. So in the morning lecture, Dr. Prabhakar has highlighted pipelining and asynchronous pipelining, synchronous pipelining, retiming. So these are not only that we are going to discuss about in the next few sessions. Pipelining and parallel processing, folding, unfolding, retiming. So there are several techniques which are available to increase the speed and reduce the power. So this is one side. And we can also use the features available with the tools, either Xilinx or Ultra, to further increases the speed and reduce the power. So how effectively we can use these features and where we have to use. Now in general, depending upon our requirement, we can explore these features so that our design will get higher speed and low power. So that's why we are going to discuss about the architecture of FPGA. So the architecture, we must know the architecture thoroughly. Because suppose for example, if you take a multiplier, we know the multiplication. So general multiplication is A into B. Okay. But then why there are different multipliers or exits? Carry save, carry ripple, Braun array multiplier, Bahuli multiplier, Wallace tree multiplier, Dada multiplier. So, and dedicated AND and XOR array multiplier, constant coefficient multiplier, systolic array multiplier. So there are different because of they are slightly varying the partial that architecture so that they are getting higher speed and lower area. So that's why there are different multipliers. Even without multiplication, by using shifting and adding, we can perform the multiplication. So CARDIC, that is a separate algorithm, distributed arithmetic algorithm. So if you are using CARDIC, suppose for example, if you take CARDIC, that is coordinate rotation digital computer, which is used for vector to polar and polar to vector or real to imaginary. Okay. So without using the multiplication, by using shifting and adding, we can perform the operation so that the number of logic gates which are reduced, the number of logic cells or number of CLBs. We are going to discuss about what is CLBs so that I can increase the speed and reduce the power. So that's why today we are going to discuss about the architecture of FPGA. So we have to familiar with the technique as well as we have to familiar with the tools. Then we can efficiently design a circuit. So first we are going to discuss about that Spatron 2 FPGA. So the Spatron 2 is not a old one, is not a new one. Okay. So it's in general Spatron 2 is a 6 members family because there are different device capacities. This is shown in the table, first column, that is XC2S15, XC2S30, XC2S50, XC2S100 and finally XC2S200. Here XC stands for Xilinx chip, 2S stands for Spatron 2 and the 15 is the device count, that is 15 into 1000, 15K. So 15,000 gates are available for this particular device. Similarly, for XE2S 200 means 200 into 1000, so that 200K devices gates are available for this particular device. Suppose my design occupies 16,000 gates. If I am using only XE2S 15, I am not able to simulate or synthesize my, I am not able to synthesize my design because my device capacity is only 15,000. But I have 16,000 gates I am using in my design. So that you have to choose the next one, XE2S 30, to verify your design. So FPGA stands for Field Programmable Gate Array. So it's a reprogrammable device. I don't want to go in detail. So what are the advantage of FPGA is, suppose for example, my design is an AND gate. So I have to verify the AND gate so that I can use the IC 7408 to verify the functionality of my design, 2-input AND gate. Suppose I want to test an OR gate, so I cannot use 7408. Okay. But in FPGA, whatever the design you want to verify, you write a code that is called hardware description language. So either Verilog or VHDL. VHDL stands for VHSIC HDL, that is very high speed integrated circuit hardware description language. So that you can write a program and then verify through simulation, you can verify the functionality. If it is okay, then you have to download the design onto the FPGA. Then your FPGA is act as an AND gate. So similarly, you can implement a microprocessor or microcontroller or DSP, whatever you want, you can implement in FPGA based on the device count. So there is no need of particular chip to verify the functionality of your design. So I don't want 7408 to verify the functionality of AND gate. I have a FPGA boards so that I can write a Verilog or VHDL code. Okay, then my particular FPGA is acts as a AND gate. So similarly, you can design any circuit depending upon your requirement. So this XE2S 15, as I said, 15,000 gates are available. Actually, in addition, we have PQ208. PQ is the package. There are different types of packages are available. And 208 is the number of IO pins, input and output pins. So normally on the top of the FPGA, so this number has written XE2S15PQ208. XE stands for Xilinx chip, 2S stands for the Spotron 2 device. Similarly for Spotron 3, 3S. And 15 is the number of device count, as I said. Then PQ208 is the number of output pins. Suppose for example, if you take a 7408, you have 14 pins. So all the 14 pins are not used as a IO pins. Okay. Some of the pins are voltage VCC, some of the pins are ground. The remaining pins are 1, 2 are input, 3 is output, 4, 5 is input, and 6 is out, like that. Okay. So similarly here, all the 208 pins are not dedicated to IO. Okay. Some of the, apart from that, we have a VCC, ground, a power bank is available for different stage levels. And clock pins are available. Okay. So which pin is used as a input pin or output pin? From the manual only we must know. Suppose 208 pins, suppose pin 50 is connected as a input, or pin 60, P60 is connected as output pins. From the manual only we can identify the input and output pins. Okay. Next one is the logic cells. Actually, the structure of Spotron to FPGA is row and column wise. There are 8 rows and 12 columns for the device XC2S15 family contains. So that's why in the fourth column I have written R cross C. This R represents row, C represents column. So there are 8 rows and 12 columns. So total 8 12s are 96. So that the number of CLBs are 96 CLBs. And the system gates, that is the third column, as I said, there are 15,000 gates. And the number of logic cells, in the next slide we will see what is logic cells. So we can call it as a logic cells or logic elements. Okay. Next one is the maximum available input output pins. There are 96 input and output pins are available for this particular device. Apart from that VCC, ground, clock, etc. Next one is the total distributed RAM and block RAM, the last two columns. That is the capacity of the memory storage. So in before Spotron 2, actually we start with XE3000, XE4000 type FPGAs. We don't have block RAM facility. We have distributed ROM. What is the difference between distributed ROM and block RAM? We will see. But nowadays we have a block RAM facilities. Previously we don't have a block RAM facilities. So the maximum storage capacity for each device is represented in the table. 16K for XE2S15 and 24K for XE2S30 and 56K for XE2S200. So the number of block RAMs also varying depending upon the device. So from the manual only, after seeing the architecture, we can identify the number of block RAMs. Usually block RAMs are placed in the left side and right side of the FPGA. So we will see in the next slide. Okay. So as far as this table is concerned, as Spotron 2 has 6-member family because of there are 6 different device counts starting from XE2S15 to XE2S200. And depending upon the device, the number of logic cells, system gates, number of CLBs, IO pins and block RAMs are varying. For XE2S15 is concerned, it has 8 rows and 12 columns of CLBs. CLBs stands for configurable logic blocks. And number of IO pins are 86 and the total block RAM capacity is 16K. So this is the Spotron 2 architecture, that is FPGA block diagram. So as I said, there are 6-member family. So this block diagram shows XE2S15. So in the previous slide in the table, I have mentioned 8 cross 12, that is 8 rows and 12 columns. So you see the CLBs are configurable logic blocks, that is 8 rows and 12 columns are there. Total 96 CLBs are there. And the 4 corners of the FPGA have written DLL. DLL stands for delay locked loop. In Spotron 3 and other FPGAs, they have written DCM. DCM is the delay clock manager. In Ultra, In Altera, we call it as PLL, that is phase locked loop or phase clock manager. The functionality is same. So DLL stands for delay locked loop. What is delay locked loop? I will explain later. So the left hand side, right hand side and top and bottoms are IO pins. So in the PPT I have written IO logic, input output logic. So in between the IO and CLBs we have block ramps. So for XC2S15 there are 4 block ramps, 2 at the left hand side and 2 at the right hand side. Each one has capacity of 4K, so that 4 plus 4 in left hand side and 4 plus 4 in the right hand side. So totally we have 16K. So that's why in the table I have written against XC2S15 the block RAM capacity is 16K. So in addition, at the center, top and bottom of the FPGA we have a clock pins, 2 at the top and 2 at the bottom. It is not shown in the architecture. Actually, each FPGA have a dedicated clock sources. Suppose for example, if you take this XC2S15, it has 25 megahertz, 40 megahertz, 50 megahertz. So depending upon our requirement, we can use the jumper to get a particular frequency. There are different frequencies are available with each FPGA architecture, that is called a system clock. So for this particular device, Spotron 2 is not same as Spotron 3 or Vertex. And similarly for Altera, if you take Apex or there are Cyclone 2, there are different FPGA kits are available. So from the manual only we can identify the clock frequency. That is the FPGA system clock frequency. So the CLB stands for configurable logic block, as I said. So the CLB is a heart of the FPGA. Okay. Actually, in Spotron 2, each CLB have 2 slices. One is S0 and another one is, we call it as S1. And each slice have 2 LUTs. LUT stands for lookup table. Actually, LUTs are the heart of the FPGA. That is the right instead of CLBs. So LUT stands for lookup tables. So 1 CLB is equal to 4 LUT. So I will repeat once again. Each CLB have 2 slices. One is S0 and another one is S1. Each slice have 2 LUTs. So that there are 4 LUTs for 1 CLBs. So you count here, we have 96 CLBs. So 96 into 4. So LUT stands for lookup table. It is nothing but it is a 4 input function generator. LUT is a 4 input function generator. So LUTs are function generator means suppose I am writing a code for AND gate. So this LUT, whatever we have written, that operation is performed by the LUT. So not only that's why it is called as function generator. In addition to the function generator, that each LUT can provide a 16x1 synchronous RAM. 16x1 synchronous RAM. So that if we combine 2 LUTs, we can create a 16x2 synchronous RAM. If we combine two LUTs, we can combine 16x2. Suppose if we combine 4, so either you can perform 32x1 synchronous RAM or 16x1 bit dual port synchronous RAM. RAM stands for random access memory, so you are all familiar with that. So I'll repeat, LUT stands for a function generator. It's a 4-input function generator. So whatever the program we have written, suppose if it AND gate means that y is equal to a dot b, that function is implemented by this LUT. That's why it is called as function generator. In addition to that, we can use LUT as a synchronous RAM. So that's why, suppose I want to, okay, in FPGA architecture, FPGA board, we have dip switches as well as LCDs and LEDs. Suppose I have, depending upon the board, it is varying the number of switches. Suppose I have 8 switches, dip switches. Suppose I want to test a 8:1 mux. So I can give the input of 8 to the switches and select line, or 4:1 if you take simple. And for select line also I can use the switches. And the output I can use an LED or LCD. So there are 8 or 10 LEDs are available. So that I can vary the switches to verify the output. Suppose beyond that, I have my design have 16x16. So in that case, or I want to verify the outputs. The outputs are more than, there are 15 outputs and each have 4 or 8 bits each. So by LED or LCD, certain limit only I can verify. Beyond that, I cannot verify the output by using LEDs or LCDs. Okay. So that's why we are using the block RAM and distributed RAM. So block RAM, as you have seen in the FPGA architecture, we have that facility. Where is the distributed RAM? So that's why each LUT can perform a function generator as well as a distributed RAM, so that I can store the data in the LUT. So what is the disadvantage of storing data in the LUT? Suppose I want to verify my design is a 8x8 multiplier. Okay. So that depending upon the 8x8, there are 15 outputs. So these 15 outputs are stored in the LUT. So my design block occupies, my 8x8 multiplier occupies some LUTs. For storing the data, I am using LUTs, so that the number of LUTs are increasing. So my design occupies some LUTs as well as I am storing the data in the LUT using as a distributed RAM, so that it occupies additional LUTs, so that the area is increased. Once if area is increasing, power is increased. So to avoid that, we are using block RAM. Previously, we don't have such facility. Block RAMs are not available. So that's why we are using LUT as a storage element. But it occupies additional area for testing the design. Okay. So nowadays we don't have that problem. We have a block RAM facility. So using block RAM, I can read or write the data. So in block RAM also there are different types: single port block RAM, dual port block RAM, and 3 ports block RAM. So single port block RAM means either I can read or write the data in the block RAM. Simultaneously, I can't do read or write in single port. Whereas in dual port, one port I can use it as a read and another port I can use it as a write. Vice versa, I can change. There are 2 ports, port A and port B. Port A for read, port B for write, or port B for write and port A for read, whatever. And 3 port is 1 port for read, 2 port for write, or 1 for write and 2 port for read. So nowadays we have 3 port. So that we are saving the number of LUTs, that is the area, so that I can reduce the power. Okay, next I will come to the clock. So I said I have my own system clock. What is the need of system clock in FPGAs? Suppose I am designing a circuit, suppose half adder. So I want to calculate the worst case delay. Worst case delay is nothing but that is the longest path delay, longest path from input to output without any delay element in between. Okay, or propagational delay. So this worst case delay may be either input to output or input to register or register to register or register to output. So which one having the maximum longest path delay? Longest path. Suppose a circuit contain different paths from input to output. Suppose for example, if you take half adder, one path is XOR gate and another path is AND gate. Okay, but anyway we are using only 2 gates. Suppose if you use full adder by using 2 half adders or using 2 XOR and 3 and or. Okay, so in such cases the number of paths may vary depending upon our design requirement. So that without a delay, here delay means register, without any register, which one is the having the longest path? So we have to calculate that path delay. For example, if it is 5 nanosecond, for example. So I have to fix a clock 5 nanosecond, then only my circuit will work. Above 5 also it is good, but less than 5 it is not possible. I will get only the partial output. Okay. So after, depending upon my design requirement, after synthesizing, the tool will give what is the worst case delay. The tool automatically calculate, or for depending upon the FPGA architecture, each LUTs have, suppose in my design I am using 2 LUTs, suppose for example half adder, 1 LUT for XOR gate and 1 LUT for AND gate, and I know the input pin, suppose P10 is connected as P1011 as connected as input and some carry or some P1314. So P11 to that LUT and P12 to another LUT. Okay, so what is the delay I have to calculate from the architecture, and what is the LUT delays are fixed, but input pin to LUT delay may vary. So through I can open the floor planner, the tool will give what is the delay from input pin to that LUT, and similarly from LUT to the output pin. We can also cross check whether the tool gives the exact delay, but simulations are always not a perfect method. We can verify the initial whether our circuit is working or not, but the actual delay is different. Okay, but the actual delays are different due to several things: process variation, temperature variation, or logic variations. Okay, so after downloading the design, then only you can say my circuit is operated at this much of frequency. So you have to verify your design. By simulation, it is not an exact method because simulations are always considered the worst case delay. But actual delay is different due to several reasons: process variation or temperature variation or logic variation. Suppose I am testing a 16 cross 16 multiplier, all the inputs are 0, then suddenly I am changing all the inputs are 1. Okay, this is also creates some problem, some variations. So that the actual method is, after synthesizing, I have to download the design on FPGA and use the system clock to verify whether my design is working or not. So that I need a clock frequency for testing my design. In simulation, we have a clock sources, so that I am connecting the clock pin, so that, and I fix 10 nanosecond or 5 nanosecond, and I am verifying the output. But after downloading, how can I feed the clock to my circuit to verify the design? That's why I have to use the system clock. So the frequency, at what frequency I have to fix for my design, I have to feed for my design. So that's why we have to see the worst case delay reported by the tool. So this worst case delay is calculated by the tool by longest path delay in your circuit between the input and output, or input to the register, or between the register or register to output. This is called as worst case delay. Okay, that is the longest path delay. Normally we call it as Dmax or Tmax. So Dmax is the longest propagation delay and Dmin is the shortest propagation delay. Or in some textbook they can put Dmax, and some textbook they can refer as, they are referring as Tmax. So Tmax is the longest propagation delay and Tmin is the shortest path delay. So that, suppose the worst case delay is 10 megahertz. Okay, so I can fix the clock frequency as 10 megahertz. Then suppose I am designing a counter, 4-bit counter. So the counter starts incrementing on each clock. So I have to feed the clock signal to the counter so that the counter starts incrementing. So I have to use the system clock for this one. Okay, so that's why we have four system clock frequencies, different clock frequencies, 2 at the top and 2 at the bottom of the FPGA. At center top, okay, at the center top we have, here at the center top we have 2 clock pads. Okay, and we have a clock distribution circuit. Why we have a clock distribution circuit? Suppose I am using the first CLB, my design is connected with the first CLBs and the 96th CLBs. Okay, first CLB and 96th CLBs, suppose for example. Suppose if I am connecting the clock, there is a delay. First CLB will get earlier than the 96th CLB. This is called as clock skew. Clock skew is nothing but arrival of clock from one point to another point. That is called as clock skew. So I want to distribute the clock,
excuse me, sir. Sorry for the
equally to
interruption.
the all. Please.
Sir, we
Hello?
are getting the same slide. Now only slides are changing, sir. Thank you.
No, actually still I am in the first slide only. Third slide only.
Okay, sir. Okay, okay, sir. Okay, sir. Okay, sir.
Yeah, I will In the next few slides, you can see all those things. Okay, this is introduction. In depth, I will explain. Okay.
Okay, sir. Okay, sir. Thank you.
So I want to distribute the clock equally to all the CLBs, then only to avoid the clock skew. So that's why we have a clock distribution network. Okay, fine. Then already I have a clock sources, 2 at the top and 2 at the bottom. Then what is the need of this DLL? DLL, as I said, delay lock loop, and or DCM, delay clock, or PLL, phase clock. Suppose I have a fixed clock frequencies in system clock, suppose 28 megahertz, 30 megahertz, 40 megahertz. Okay. Suppose my circuit is operated at 10 megahertz or 100 megahertz, but I have only 25 megahertz frequency. But I want to test my design. My design is operated at 100 megahertz. So how can I test my design? Because I don't have the system clock. That's why we are using DLL. So DLL can be used to increase the clock frequency. Actually, through programming, we can divide the clock frequency, but we cannot increase the clock frequency. How can we divide the clock frequency? Suppose you see the counter, a 3-bit counter, 0, 0, 0, 0, 0, 1, finally it is 1, 1, 1. So you see the first column, it is alternate zeros and ones, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Okay. So 1 on and 1 off. Okay, 0 means off, it's an off period, and 1 means on period. You see the second column, middle, there are 2 zeros and 2 ones. There are 2 off periods and 2 on periods. Suppose if on period is 1 nanosecond, for example, if you take off period is 1 nanosecond, means in the first case I have 1 on, 1 off. So totally I have 2 nanosecond. If you see the middle row, I have 2 middle column. There are 2 zeros and 2 ones. So that 2 nanosecond is off, 2 nanosecond is on. So it is 4 nanosecond. Previously it is 2 nanosecond. So 1 by 2 is 50 megahertz. And whereas next one is 1 by 4, 25 megahertz. So I am dividing the clock frequency. You see the third column, there are 4 zeros and 4 ones. So 4 nanosecond is off and 4 nanosecond is on. So that totally 8 nanosecond. So 1 by 8, approximately 16 or 15. Okay. So that 50, 25 and 16. So through designing a counter, I can divide the clock frequency, but I cannot multiply the clock frequency through programming. That's why we go for DLL. So DLL is not only used for multiplying the clock frequency, also we can divide the clock frequencies. Okay, suppose I have a 10 megahertz clock source in FPGA. I can use a DLL to either increase. Actually, DLL has fixed ratios of clock. 1 multiplied by 2, 2.5, 3, 4.5 like that. So from the manual only we can identify. Similarly, we can divide the clock frequency. So 10 megahertz means I can use 1 DLL to multiply to generate 20 megahertz. Or maximum, suppose I have the ratio is 4 means 40 megahertz I can generate by using 1 DLL. Similarly, I can use another, I am combining with another DLL to generate 80. Then I can combine with the third, I can generate 160 and then third and then 320. That is also possible. I can combine all the 4 DLLs to multiply the clock frequency or divide the clock frequency so that I can test my design. So not only the DLLs are used to either increase or decrease Also we can phase inversion is also possible. 30, 45 degree, 90 degree, 180 degree, 360 degree phase inversion is also possible. So what is the difference between, what are the additional advantage in Altera compared to Xilinx? In Altera we can fix, suppose I want to multiply, in Xilinx the ratio is fixed, the multiplication factors are fixed in each DLL, 1.5, 2, 2 like that. Suppose I want to multiply 1.25 or 2.25, 2.225, that is possible with the Altera FPGAs. So these are the features. Okay, so DLL, block RAM, and we are going to discuss about the further features available with that. So this is the general block diagram of Spatron 2 FPGA. Now this is the internal block diagram of input and output block. So previously we have seen the four corners, that is, sorry, in the left side, right side, top and bottom are IO block. Okay, so these are the internal architecture of input and output block. So this input and output block consists of three registers, either edge triggered or level sensitive. So it is shown in the figure. So first one is TFF. So this can be used to register the signal that controls the programmable output buffer. And the next one is the off register. So I have written off, the middle one. This can be programmed to register a signal from the internal logic. And third one is the bottom, which is used to, the device can register the signal coming from the IO pad. And we are using a common clock for all the three. Not only that, we have a independent clock enable, EC, that is shown in the diagram. And in addition to the clock and control signal, the three registers have sharing the set and reset, SR. I have written in that SR. So for each register, this signal can be independently configured as a synchronous set, a synchronous reset, an asynchronous preset, or asynchronous clear. Also we have a pull up and pull down resistor and weak keeper circuit. So the weak keeper circuit is connected to the each output. When if it is selected, the circuit monitors the voltage on the pad. Suppose if it is low or high, it matches the input signal. Also we have a ESD, that is electrostatic discharge option is available, and over voltage protection is also available. So which is, both are used to, suppose if there is any higher voltages, suppose if more than 5 voltage, actually we are giving 5 voltage, but 3.3 volt is sufficient for FPGA. If it is more than 5 voltage, we are using a Zener structure to ground so that it reduces the voltage. Suppose if it is low, similarly it can increase the voltage. And we have a input path and output path. A buffer in the input path routes the input signal either directly to the internal logic or through an optional flip-flop. there is a delay element, programmable delay. So this delay is matched to the internal clock distribution delay of the FPGA, and to avoid any pad-to-pad hold time. Unnecessary delays can be avoided by using this programmable delay. Similarly, we have an output path. The output path contains a programmable output buffer. Buffer already you are all familiar. So the output signal can be routed to the buffer directly from the internal logic or through an IOB. So I can use this input and output pin. Either I can connect this input pin to the switches or to the LEDs or LCDs, or I can feed the signal. I can feed the input through 8255 programmable peripheral interface. That is also possible, but we have to be very careful. Suppose if there is any short circuit, then your device is damaged. So we have several voltage, VCC, VCCO, and actually the bank of voltage. Normally we are saying that bank of voltages are available. 3.3 volt, 2.5 volt, 1.5 volt. There are different voltage levels are available. So, okay, in general, just you want to know what is the internal architecture in the input and output pin. The input and output pin have 3 flip-flops and 2 buffers. One is programmable input buffer and another one is the programmable output buffer. And there is a voltage protection circuit is available to avoid the excess voltage. And suppose if it is any low voltage, there is a beekeeper circuit to increase the voltage level. This is a general block diagram. Actually, this is important. This is the internal block diagram of CLB, that is configurable logic block. As I said, each CLBs have 2 slices. So this is one slice. This block diagram shows S0, that is slice 0. Similarly, we have slice 1. So as I said, each slice have 2 LUTs. Okay. Normally we call it as FLUT and GLUT. Okay. In addition to that, we have a carry and control logic, and here also we are using 2 flip-flops, D-type flip-flops, either level sensitive or edge sensitive. The D inputs can be driven either by function generator within the slice or directly from the slice inputs. Actually, here, as I said, it's a FLUT or GLUT. Okay. So because the inputs are F1, F2, F3, F4 for FLUT, and for GLUT, G1, G2, G3, G4. In addition to the LUT, so as I said, LUT is a function generator. Not only the function generator, we can store the data. So here you see there is one addition to that F5. One input I have connected with the carry and control logic. Okay, F5 in. This is the one F5, and F6 actually it is not shown because it is combined with all the 4 LUTs, both the slices. Okay, F5 and F6. So this F5 and F6 are call it as an additional logic. So using this F5, I can implement any 5 input function or 4:1 multiplexer, or I can implement here any 9 input. Similarly, F6, I am combining all the 4 LUTs to perform a 6 input function or 8:1 max or 19 inputs. See why I am telling, because we have enough LUTs, and depending upon the device, the number of LUTs varying, but how effectively we can design. So what is the need of this carry and control logic? Suppose I want to implement a full adder circuit. Suppose if there is a carry, if all the inputs are 1, so that carry is 1. So this carry occupies an additional LUT. So to avoid that, I am using the carry chain. This carry and control logic is the XOR chain. So that I am using this XOR chain to avoid the additional LUTs occupied by the carry bit. So by the way, I can effectively and efficiently designing my circuit so that I can increase the speed and reduce the power. Okay, so that's why the effective design. Simple example I am telling. Suppose I want to implement an AND gate. How effectively I can design? So I know if 0 0 output is 0, 0 1 output is 0, 1 0 output is 0, and 1 1 output is 1. Okay, A dot B. So that how effectively I can design? Is it possible to reduce the number of input combinations? So I have 4 combinations: 0 0, 0 1, 1 0, 1 1. So I want to reduce the number of combination. 1 minute. Sir, sir 2:30 sir unga session 2:30 sir. இன்னும் அந்த இது வரல சார், உங்களோட ப்ரொஃபைல் இன்னும் வரல சார். ஆமா சார், நான் இப்ப செஷன் எடுத்துட்டு இருக்கேன் சார், முடிச்சிட்டு உங்களை கூப்பிடுறேன் சார். தேங்க்யூ. எஸ் சார், ப்ளீஸ் சார். Okay, so there are 4 combinations: 0 0, 0 1, 1 0, 1 1. So is it possible to reduce the number of combinations? That is, then I can effectively write my code. Efficiently I am designing my circuit. So how can I effectively do? If any one of the input is 0, output is 0. If both the inputs are 1, output is 1. Instead of using 4 combination, I am writing if any one of the input is 0, output is 0. If both the inputs are 1, output is 1. Then I can implement the AND gate. This is what I can effectively writing the code. So that this carry and control logic, there are 2 carry chains, XOR chain. So even without using the lookup table, I can use these 2 carry chains to implement a 1-bit full adder. Okay, so normally for carry bit, we can use this carry chain to avoid the additional LUTs occupied by the carry bits. Okay, so that using this F5 and F6, I can implement maximum 19 input selected function by combining all the 4 LUTs, or by combining the 2 LUTs, I can perform selected function of up to 9 inputs, or I can perform 4:1 max or 8:1 multiplexer. And we have F6 is not shown because I have to combine all the 4 LUTs. So this carry and control logic is nothing but that is the arithmetic logic. That is what, as I said, the arithmetic logic includes an XOR gate that allows 1-bit full adder to be implemented within the logic cell. So whatever the program I have written, suppose AND gate means this A, B are inputs and Y is output means, suppose I am using the tool is using the GLUT means G1, G2 are connected to A and B and Y is connected to the output in O. So that this LUT is act as an AND gate, so that my FPGA is function as a AND. So this is what I have explained. LUT, that storage element is the 2 registers we are using, and additional logic 5 input, 9 input, and arithmetic 2 carry chain. So I can implement a 1-bit full adder. Okay, this is the next block RAM. So this is dual port block RAM. Okay, so dual port consists of, as I said, port A and port B. So port A, the upper half is the port A and the bottom one is the port B. So WE stands for write enable for port A and enable, reset, clock, address, data input and data output. Similarly for port B. So that I can use port A for write and port B for read, or port A for read and port B for write. So if I am writing the data into the RAM, so I have to write enable is high, then read. Okay. Suppose if write enable is 0 means I am reading the data. I am reading the content from the block RAM. Okay. So if write enable is high means I am writing the data into the RAM. I am storing the data into the RAM. If write enable equal to 0 means I am reading the content from the RAM. Enable and reset, these are all optional. Okay, if you want you can use, and you have to feed the clock, then only you can read the input or write the data into the RAM. And data input, so you have to feed the data, and data output also. Suppose if you want to retrieve, you can use data output. Similarly for this one, this is called. So on the top of the diagram I have written RAM B4S/ and -S/. So there are two ways to I can use the block RAM. So I can use the primitives. There is a block RAM facilities are available. Either I can use primitives. These are all primitive. Straight away I can use RAM B4 means this particular RAM can be used. Or I have to use the core generator. Okay, or MegaWizard plugin manager to explore the block RAM facilities. So these are the different block RAMs available with the SpotRun 2. This is what we have seen in the first slide in the table. So the total block RAM capacity is 16K for XE2S15 and 56K for XE2S200. The number of block RAMs is I have given in the middle of the table. So for XE2S15 there are 4 block RAMs. So you have seen 2 at the left and 2 at the right. For XE2S30 there are 6, 3 at the left and 3 at the right. Similarly we have XE2S200. Number of block RAM. Similarly maximum data capacity also shown in the table. So this is the clock distribution network. So as I said, the clocks are equally distributed to the CLBs. You see 2 at the top and 2 at the bottom. Okay. So this is the clock distribution network. In addition to the clock, we have a clock buffer. Okay, as you know what is buffer. So that through buffer, the clock can be distributed to all the CLBs at equal time. So to avoid the clock skew. So this is the clock distribution. This is the inbuilt clock distribution circuits are available with the FPGA architecture. This is the very important features available with Xilinx and Altera. One is macro and another one is logic clock. And placement through UCF or manual routing, boundary scan, DLL, DCM or PLL or distributed RAM. DLL, DCM, PLL we have discussed, and distributed RAM also we have discussed, because LUTs can be used as a distributed ROM. Now we are going to discuss about macro or logic clock. UCF stands for user constraint file. Actually in Xilinx, one way of implementing the design is by writing the HDL, hardware description language. Without writing the code, Is it possible for me to implement any design? Yes, it is possible with Xilinx. Manually, I can, without writing the code, manually I can implement any design, but it is time consuming. It is not an advisable one, because if you do any mistakes, then your device get damaged. But in some cases, we need manual routing. Okay, manual connection between the two blocks. Manually, I am connecting the two designs. In some cases, it is depending upon my requirement. But these features are available with Xilinx, not with Altera. So UCF stands for user constraint file. So what is the advantage of this UCF? Okay, anyway, we will see one by one. Next one is the embedded system block or block RAM. This one this is the features are continued. Okay, previously first we start with macro or logic clock, placement through UCF or manual routing, boundary scan, DLL, DCM or PLL, distributed RAM. Then ESB stands for embedded system block or block RAM. Next one is the PC based testing, signal tap to logic embedded analyzer or chipscope pro. So the signal tap to embedded analyzer is available with Altera, and chipscope pro facility is available with Xilinx, and a system on programmable chip based circuit on both Xilinx and Altera FPGA and power dissipation. Okay, first one we will discuss with macro. Before that, first we will discuss about that UCF, then we go for macro. Actually, UCF stands for user constraint file. Suppose I want to design an half adder. So as I said, so okay, half adder contains one XOR gate and one AND gate. Okay. So after writing the code, the tool may assign any one of the CLBs. Okay. Suppose there are 96 CLBs are available for XC2S15. So that tool may assign any one of the CLBs for my XOR gate and AND gate. Okay. Suppose I want to particular CLBs for my design. Okay. So that I can use this UCF, user constraint. So I can instruct the tool to place the design whatever the position assigned by me. Suppose, as I said, there are 8 rows and 12 columns, 96 CLBs. Suppose I want 45th CLB for XOR gate and 47th CLBs for AND gate. So I can assign the position through this UCF. Once if I assign the position through UCF, then the tool assign the same place for my design. So what are the disadvantage? So manually we can also do. Okay, one is using this tool I can assign the position. Not only that, suppose if I want to assign the 4 CLBs, okay, as a square form. Suppose X15, X16, X14, X15. Suppose in the bottom again I have X21. There are four square type. Okay. So just you can mention the first and last CLB's number. Okay. So that the tool assigns only the 4 CLBs. Okay. Suppose for example there are Hello? Am I audible? Hello?
Yes, sir. Now it's audible, sir.
Actually, some network problem. Shall I continue for another 15 minutes? Is it okay for you? Okay. Thank you. So through user constraint file, I can assign the position for my design. Whereas in manual, actually this method is very easy. Okay. And in case of manual, if it is tedious, and another problem is every time, suppose if next time again I am verifying the simulation, means in manual it is not possible. Every time I have to assign the position through manually. Okay. So next time, suppose if after switch off again I have to start, means in that case it will assign some other position in the case of manual. So every time I have to do the manual process, so that it is tedious and time consuming. Whereas in this case UCF, if it is fixed and the thing is easy. But if I am, so here only the CLB positions are fixed, that is LUT positions are fixed, but in between the LUTs that interconnect delays are varying. Okay, in UCF. Okay, so UCF is not only assign the position for CLBs, also I can assign the position for my input, as well as I can assign the position for my output. Okay, LEDs, dip switches also it is possible. Suppose for example, I am designing a OR gate. So it's a 2 input A, B and C. So suppose I want to use the C15th CLBs for my OR gate. So I can assign the position for C15. Okay. And then pin A is connected to P10 of input switch, for example, dish switches, and P11 is connected to B, and suppose LED 0 is connected to P50, so that C is connected to P50. So I can assign the position for my design as well as the input and output. But the problem is, suppose I am implementing a half adder, suppose one CLB occupies, for example, one CLB is occupying for X adder and another CLB is occupying for AND gate. Okay, for example, I am saying. So I am assigning two different positions. One is P50, one is P15, and another one is P16. So in between P15 and P16, that interconnect delay is not fixed in the case of UCF. Okay. So either it may connect it directly, or because there is a programmable matrix is available between the CLBs. So that, but there is a slight variations may be there. Okay. But this, so I want to fix the interconnect delay as well as the LUT delay. That's why I am going for macro or logic clock. Macro is available with Xilinx, and Altera is available with logic. Logic clock facility is available with Altera. Or through manually I can use the macro facilities. Okay. So what is macro is nothing but, so I can assign after, suppose I am implementing a 8:1 multiplexer. So my design occupies several input and output pins as well as the CLBs. Okay, then I can use macro facilities to lock the design. Okay, to lock the design. So once if it is locked means you can download n number of times, the tool assign the same position and same delay. Okay, the interconnect delay is also fixed between the two CLBs, as well as the position of the CLBs and input to the CLBs, CLB to the output, everything is fixed, and you can synthesize n number of time your circuit, the tool assign the same place, so that it won't be varied. So why we need macro? What is the need of fixing the design? Suppose I am using a clock, fixed system clock, or I can use DLL. Okay, some beyond certain cases I have to generate my own clock frequency for testing the circuit. Okay, I want to generate. So because that's why one of the technique is available to increase the speed and reduce the power is wave pipelining. Morning Prabhakar sir said pipelining. This is another method, wave pipelining. In wave pipelining, by trial and error method, I can increase the speed and reduce the power. So trial and error method means through real time I am varying the clock frequency. Okay, so I know this my circuit is working between these two clock frequency, but which particular clock frequency, that I do not know. So that I keep on varying, I keep on changing the clock and clock skew to verify my design. In such cases, I want to generate a clock frequency. So that clock frequency is nothing but it is very simple. One NAND gate is nothing but, okay, one input is enabled and the one of the input is connected to the output. Okay, then enable equal to 1, then automatically it is changing. Okay, or AND gate and inverter. Depending upon your on and off periods, you can add more number of gates. At the end, you put one NOT gate. That's all. That output is connected to the input to the first one, so that you can generate your own clock frequency. Okay, but when you are downloading that design onto the FPGA, but tool assign every time different places and your clock frequency is not fixed. Suppose I am generating a clock from 10 megahertz to 50 megahertz. Okay, sometimes it will get 11 megahertz, sometimes it will get 9.5 megahertz, so that I cannot get exact 10 megahertz to 30 megahertz. So that I can use this macro and logic clock to fix the interconnect delay as well as the LUT delay, so that I will get the same frequency every time. Okay, this is one example. Similarly, depending upon your requirement, you can lock. That's why in Altera we call it as logic lock. We are locking our design. So what is the difference between macro and logic lock? Okay, so as I said, macro facility is available with the Xilinx and logic lock facility is available with the Altera. So what is the advantage of logic lock? Both are same, but manual routing is possible with the Xilinx. Okay, suppose I am using one clock generator, I am using one counter. So for counter I have written a program, and then my tool has assigned some places, and then I have locked as a macro 1, and my clock generator is another macro 2. So I want to link these two. That is not possible with the Xilinx. So manually I have to link these two circuit. Okay, suppose if I am using two macros in one design, that is possible with the Xilinx, but it is not possible with the logic clock. But the advantage of logic clock is there is a parent and child module. What is parent and what is child module? So logic clock also, which is used to lock your interconnect delay as well as the CLB. CLBs are logic element or logic cells. Okay, depending upon the tool we can say both are same. Okay, all are same. So what is the parent module and child module? Suppose child module is, suppose for example, I am implementing a 16-bit adder by using a 1-bit adder. I have 1-bit adder in my library, okay, as a primitive gates. Okay, so by using 1-bit adder, I can implement a 4-bit adder. I can use a 4-bit adder to implement a 16-bit adder. I can use a 16-bit adder to implement a 32 or 64. So, but my lower level module is a 1-bit adder. Okay, my lower level module is a 1-bit adder. So that this 1-bit adder is a child module. That 64-bit adder is a parent module. Suppose I want to shift. So after writing the code for 1-bit adder, that is called as structural. Structural is a detailed level of description when we are writing using either Verilog or VHD. So I am assigning the position for my entire design. Now I want to shift. Suppose for example, my design is occupied in left hand side of the FPGA architecture. Now I want to shift the entire design to the right hand side. Okay. So how can I shift? So this is possible with both Xilinx and Altera FPGA. In Xilinx we have swap. There is one option is available in the floor plan editor. Using swap, you can change the position of your design into some other design. But the design next time again it will go to the particular design only. Okay. So whereas in logic clock in Altera, you can assign the position for your parent module. Your parent module is a 64-bit adder. You can assign the position for your parent module. Your child module is also shifted into the parent module. Okay. Only thing is that space. Suppose you are using 1000 CLBs or 1000 LUTs for your total design means you have to assign 1000. Suppose if it is 900 means your child module, it is not possible to fit into the parent module. Okay. So only thing is you have to be very careful with the number of total counts. So that no need to specify for your child module. You can specify the position for your parent module. Then your child module is also shifted into the parent module. That is called as logic lock. So you are locking to your design so that you can fix the interconnect delay as well as the LUT delay. So the advantage is every time when you are synthesizing your circuit, the same delay only you are, that is the worst case delay, you are getting the same thing. Okay, because as I said, the actual delay is different, but it will give the same delay. That is the advantage of macro or logic clock. So this is what I have mentioned, logic clock. Okay, parent and child module. But in Altera manual, it is not possible. Distributed RAM already I have explained. Block RAM also. So either you can block RAM, as I already said, using primitives. I have written RAM. Yes, that is one method. Or you can use core generator or Mega Wizard plugin manager. Core generator feature is available with Xilinx, and Mega Wizard plugin manager feature is available with Altera. Okay. Next one is the boundary scan. Actually, so nowadays we have SOPC, system on programmable chip. Actually, we have a FPGA as well as processor inside the chip. Okay, so in Xilinx we call it as a microblaze processor. In Altera we call it as a NIAS processor. It is a 32-bit processor. So the advantage of SOPC is, so through processor it is simple. We can write a C program. Okay, so I can through processor I can feed the data into the FPGA, and by writing the C program, similarly I can extract the data from the FPGA to the processor. So same screen window, I can see I can feed the input as well as the extract the output by using the processor, NIAS or microblaze processor. Okay, but previously we don't have this processor available with the FPGA. So for that case, there is a feature is available with the boundary scan. So this boundary scan I can read back, okay, or continuity tester. Okay, I suppose if there is any discontinuity in the circuit, suppose there are different paths are there. One of the path I am not getting the correct out. I am not getting the correct output. So there may be a problem in the partial product. Okay, in the partial stage. So that I can verify using this boundary scan facility. This is available with the Xilinx. Okay, so that there is one controller called tap controller, that is test access port. So through test access port controller, I can read the data. Okay, whatever the output I have, so I can read the data from the FPGA. But nowadays it is not a problem because we have a process, inbuilt processor is available with the FPGA. So the advantage of boundary scan in previously, we don't have additional PC because previously we don't have block RAM. For that we are using one additional PC. Okay, in addition to that, okay, and also we are using one 8255, that is programmable peripheral interface board for reading the content from the FPGA. So that's why the advantage of boundary scan is there is no additional PC is required for testing. So DLL, DCM, PLL already I have covered. We can divide the frequency, we can multiply, and also phase inversion is possible. Next one is PC based testing. This is what additional PC. I can use a block RAM or I can use one more PC for testing the. I can extract the output from the FPGA, but this is tedious and risk. Next, this is a very good feature available with the Xilinx and Altera, that is called as ChipScope Pro and Signal Tap to Logic Embedded Analyzer. Actually, ChipScope Pro with Xilinx and Signal Tap to Logic Embedded Analyzer is available with the Altera. So these both the tools are used for on-chip verification. See, suppose I am designing a full adder circuit, but I am not getting the correct output. Maybe the first half, I want to test whether the first half adder output is right or wrong. Okay, I am connecting two half adders to implement a full adder circuit. So I am not getting the correct output at the full adder. So what I have to do, I want to verify the first half adder output whether it is right or wrong. So that real time I can verify, I can read the output of the first half adder. That's why we are using this features. So on chip verification is possible. Okay, we can also measure the clock frequency. That system clock, suppose if I am connecting, or my own clock generator I am connecting, whether that clock gives the correct frequency or not, I can measure. So one more additional window is opened in my PC so that I can view the real-time output of my design. Okay, so that's why it is called as on-chip verification. ChipScope Pro and Signal Tap to Logic Embedded Analyzer. Next one is the power measurement. So I can measure the static as well as the dynamic measure by using the simulation. So this is one BIST-based web pipeline circuit for testing additional PC, that is one method, and without additional PC through SOPC, that is using system on programmable chip. By using the processor I can verify. I don't want to go in detail because it takes time. Okay, so this one is the time consuming, and that's why we go for SOPC because it has a processor. This NIAS2 I have written. So it is Altera for NIAS2 and Xilinx for microblaze, and this is the combinational circuit. So I can feed the input to the custom block and read the input from the custom block to the processor. Okay. Any doubt you can ask or send SMS. Hello.
Participants, if you have any queries, you can ask, please. Thank
Okay.
you for your detailed and informative session.
Hello.
Thank you. Thank you. Thank you.
Hello. Hello. Sir, one question, sir.
Please.
Sir, let us say in FPGA, if I am trying to implement booth multiplication and modified booth multiplication, these two are two different algorithms, booth multiplication and a modified booth multiplication. So, but finally, it is going to map to the LUTs lookup tables. But in terms of gates and all, it's not possible, right? How it is? I mean, ASIC design when we do, that is going to map to the gates, right?
No. See, ASIC is once if you design, it is fixed. It's type of an embedded design. Okay. Whereas in
Yes.
FPGA, next time you can use for some other purpose. Okay.
Yes.
So
yeah,
whatever the design you have, okay, you can simulate it and then verify. Suppose boot and modified boot. That is what you are question, isn't it? So you can implement and you can verify the functionality and how much speed are you getting depending upon your architecture. Okay.
Okay.
Depending on architecture and how effectively you are designing the architecture is the prime thing.
Sir, one more question, sir. Suppose say if I am developing a Verilog HDL code for ripple carry adder, one thing. The other thing is carry look ahead adder, Verilog HDL code if I am developing, and these two I am synthesizing using FPGA tools such as Xilinx ISE.
Okay.
But the ultimately synthesized is mapped to LUTs, right? But I mean, area point of view, it is not going to distinguish, right?
No, actually, see, for example, suppose you are designing a carry save adder or carry ripple adder. Okay. Suppose, for example, there are 3 different modeling techniques are available: behavioral, data flow, and structural. Okay. So, in structural, you won't get less LUTs, or behavioral, you get more. Not like that. Okay. So it is not like that. So whatever the code you are writing, so the tool will implement, will synthesize, and it will give how much areas you are utilizing, how many LEDs are using, how many registers are using, what is the worst case delay between the path. Okay, this is what you are getting from the tool. How effectively writing it is up to you must know the architecture for carry save architecture and carry ripple architecture. How you are effectively writing the code, that is you researcher's job.
Okay,
Whatever
sir.
you are giving, the tool will give the report. That's all.
Okay, sir. Okay. Thank you.
Thank you. Okay, thank you.